I'd like to cover a bit of background material and say a couple of words about deconvolution. With the mass hunter deconvolution approach, an important point is that these algorithms are integrated into the mass hunter applications, qual and quant. The algorithm uses the parameterless integrator features such as noise, discrimination, spike rejection, and peak metrics. Also, this is basically targeted at GCMS scan data. This is similar to AMDIS, and let me take a moment to thank the AMDIS and the NIST library search teams for their excellent work. This approach is generalized so that it will handle both MS and MSMS scan modes, for example, product ion scan, and it has been generalized to handle a higher mass accuracy as well. The purpose of deconvolution is basically the part that's an algorithm that extracts pure component spectra from complex chromatograms. And as always pointed out, there's four major steps. The noise analysis, which I mentioned being done by the integrator. There's component perception, spectral deconvolution, grouping the ions together that fit a model peak shape, and then last, using the library to do a compound identification, spectrally matching. Here is an illustration of a deconvoluted chromatogram. I've got the TIC, the total ion chromatogram, at the top, and next I'm showing you what it would look like deconvoluted. So you'll see that there's colored peaks which are showing the ions that group together in this model peak shape. There's a blow up down here, and you can see that a number of these components end up coeluting at the same time, but different retention times, enough so that they can be separated and grouped together in this model peak shape. Here there's two under this last peak here, compound 2 and compound 3, once they've been identified. Here's another illustration which shows the TIC and the components underneath. And you can see from this illustration that the spectra can have contributions from several components at the same ion. And is often the case, there's matrix background in these chromatograms, and that can contribute to the peak, as well as interferences, as you can see, that could contribute to the peak. So now you can see from this illustration the contribution of deconvolution, which can draw out the spectrum of the target even though there are interferences or matrix that are coeluting, so that you can get a spectra to compare with the library. Last, let me mention the parameters that are associated with deconvolution. There are a number of them. Let me point out the peak filter parameters. You can exclude certain masses from involvement in the deconvolution algorithm. Or, for example, you could say I want to have the peak having a certain threshold or a certain signal to noise threshold that is required for me to return that as a peak from the deconvolution algorithm. This gives you a little bit of control to tune this to the kind of data that you require.